Hey friends, it's good to be back with you. Oh, there you are. It's good to be back with you, and today I want to talk about how to calculate pi. Why do we want to do that? Well, there's a reason. First, let's talk a little bit about pi, the number. Pi is 3.14159265359, and it goes on forever. It does go on forever. Pi is an irrational number. It is the ratio of the circumference of a circle to the diameter. You just go around the circle, divide by the length across it, that's pi. And pi is absolutely everywhere. It seems to be just about woven into the fabric of creation. If you look at the equations for general relativity, there's a bunch of tensor stuff, and on the other side of the equal sign, there's a pi. It's there. Well, that's about as fundamental as it gets, I think. And it crops up absolutely everywhere in our calculations. You just can't get away from it. So we know, I looked this up, we know 63 trillion digits of pi pretty much right now, and I think Google is shooting for 100 trillion. Why? Well, the utility of it is, there supposedly is some, let's just say it that way. Now, the circumference of the Earth is about 40,000 kilometers, so that's 40 times 10 to the 6th meters. The diameter of a hydrogen atom is about 10 to the minus 10 meters. So if I know 18 digits, say, of pi, I can confidently express the circumference of the Earth to within the width of a hydrogen atom. Now, maybe as a physicist or something, I would care, and I might have very good reason to do so. As an engineer, I'm out. I don't care anymore. That's plenty. So 18, 20 digits of pi is plenty for any practical engineering purpose. Yet we know 100 trillion, and we'll probably know more. We're shooting for 100 trillion, and we're probably going to go beyond that. Now, the people who do this will tell you that the reason we know this many digits of pi is either to explore the distribution of the digits, which is like a number theory problem, or that when people develop new computers, one of the tests they perform on it is to have it calculate all these digits of pi. The idea that if your computer is working correctly, that is, the circuits and the software and everything are working correctly, you should be able to do these very, very extensive calculations and get the right answer. If you subject it to this test and you don't get the right answer, something's wrong. That seems practical enough. But I don't think that's the whole story. My hunch is we're doing this just because we want to. It's the same reason we paint pictures. It's the same reason we write poetry. It's the same reason we solve crossword puzzles. We just want to, and that's a good enough reason. So, if people are doing this, how is that? Well, we're going to explore this a little bit. I'm not going to go too deep into it. And the reason is I want you to learn about how algorithms work. Now, we already know what pi is. We're not going to calculate anything we don't already know. But the means by which we do it, that's what's important, right? And so we're going to go over a couple of algorithms, and I'll ask you in the homework to program a couple of them. So the algorithms proceed. There's about 4 levels pretty much of algorithm. The first is when you start drawing circles. Well, one of the first algorithms we know of was by Archimedes, and he did this to calculate pi. And it's pretty clever, actually. It has a lot of the properties of a good algorithm, and we'll learn about that. The next one is we're going to use trig functions. Well, let's see, there's 2 pi radians in a circle, so it isn't too surprising that trig functions might show up when you're calculating pi. This is a little less obvious. Now, this is relatively intuitive. As soon as you see this, you're going to go, oh yeah, that ought to work, and it does. This one is a little less intuitive. There's a thing called Machin-like formulas, and I don't know how to pronounce this guy's name. I hope I'm getting it right. Formulae. So Machin-like formula. And the last ones, I'm just going to class as magic. They're not magic. They're very firmly grounded in mathematics. But some of them I don't quite understand how they work. So it's not really magic. I shouldn't do that. Seems like it though. So we're going to go through these 3 and then we're going to stop, because by then you'll see how algorithms, these examples of algorithms work. You'll see the properties they have, and you'll see how efficiency matters and how you measure efficiency. And that's what we really care about. We're calculating pi mostly because it's fun, and partly because we know what the answer is. We're going to know if our algorithms work or not. So let me clear out my board here, and we'll get started with the drawing circles, the Archimedes method. Okay, to start, let's look at the method Archimedes developed for estimating pi. Now, this is one of the first, if not the first, algorithm we know about, and it's pretty good, except for one thing. But it's got a lot of properties we want in an algorithm. It's easy to describe, it's not too hard to implement, it converges on the right answer, and better yet, it gives an upper and a lower bound estimate of the solution. So when you go through the process, you'll know not only your estimate of the answer, but you'll also know how good that estimate is, and that's really important. The thing it doesn't do very well is it doesn't converge very quickly, and we'll talk about that here in a bit. So here's the beginnings of it. Let's take a circle that has a radius of 1. Now we know that the circumference of a circle, and I'll just call that S, is pi times the diameter. That means pi equals S over the diameter, and here that means it's S over 2. Now this is going to work no matter what size the circle is, because if you scale the circle up, the circumference and the diameter go up proportionally. So pi is always the ratio of the circumference to diameter, whatever size the circle is, it doesn't matter. So this is important. In fact, I'm going to put this up here because we're going to reference this again. Pi equals S over 2. All right. So all we got to do now is if we could estimate S, we could estimate pi. All right. So here's what we're going to do. This is what Archimedes did. Is I don't know how to calculate the length around a circle, because what's calculus? Remember, it was 20-some hundred years ago. He didn't have a chance at that. But what I do know how to do is I do know how to work with polygons. In particular, let's start with a polygon of 6 sides. So I can say, let's see, where's my, there we go. All right. So S is approximately NL, where L is the length of one of these sides. Okay? If I knew what L was, I could approximate S with it. All right? Let's take a look at one of these triangles here. All right, let's see if I can draw a 60-degree triangle here. It's not exactly, actually it's pretty close to 60 degrees. So this angle right here, theta, is 360 degrees over n, where n is the number of, again, the number of triangles we're dividing the circle into. And I'm going to divide it into 2 equal triangles here. So I'll call that side x, and I'll call this side r, and that's 1. That's the radius of the circle. In fact, I'm going to put the x on the inside here. And so here's where the circle, how the circle intersects this triangle. Okay, so there's where the circle goes. So you can see how the triangle is oriented here. Well, this angle here is theta over 2. Now, it seems like there's a lot of sort of bookkeeping going on here. So where we're trying to go with this is if I could estimate L, I could estimate S, and if I could estimate S, I could estimate pi. In fact, let's go one step here. If S is n times L, this is approximately NL over 2. Okay? So I've got a way of estimating pi. I just need to know what L is. And the closer L is to that section of the circle, the arc length of that section of the circle, the closer my estimate's going to be. So how about this? It looks to me like I can say sine of theta over 2 equals x over r. Well, r equals 1. Let's see, theta over 2. If theta is 360 degrees over n, then theta over 2 is 180 degrees over n. Okay, I'm going to do this in terms of n, because where we're headed here is if I can figure this out for n equals 6, and I can get about the right answer, what if n got bigger? This is what Archimedes did. This was one of the great insights he had. All right, so let's figure this out. So it looks to me like x equals sine 180 over n, and that's because r is 1. Okay, that means L equals 2 sine 180 degrees over n. All right, so let's see. Now I know L, so NL over 2. That 2 is going to disappear. Isn't this great? All right, so pi is approximately, so let's put the L, this L in here and divide it by 2. I'm going to get n sine 180 degrees over n. Now, there's an obvious problem with this. Now, I put 180 degrees in there to try not to get us too far afield, but that's really pi radians, isn't it? So you kind of got to work with pi to get pi. It's not as big a problem as you might think. Okay, so have we overestimated or underestimated pi? Well, we've underestimated it because the length of the circumference of the hexagon is smaller than pi. All right, well, that's the inscribed solution. What if I were to draw a hexagon on the outside here? Let me do that in a different color. I'm not going to draw all of it because it's going to get too busy here, but you get the idea. Right there. Okay, I could draw another hexagon that way, and this is called a circumscribed hexagon. Well, can I do something like this with that? You bet I can. Let's try it. Now let's see, what am I going to keep here? I'm going to keep that. I don't need this anymore. Can you remember n times sine? We'll need that here in a little bit. Okay, same triangle so far. We're going to make one change. We can get all the nomenclature in here. I'll name everything. Okay, so we're back to where we were before. But remember where the circle was outside the triangle? Now it's inside the triangle. So the circle now looks like that. And that's not the radius, this is. So now that's 1 and that's x. So we've got a trig function, we've got another trig function, though, a different one. So now I can say that x over 1 is tangent theta over 2, all right? Or x equals tangent theta over 2, because 1 is the radius right there. In fact, if you want, we'll put radius in there and we'll let it go to 1 to get that. So we're going to go through the exact same argument, and what we're going to find out is, write this out because this is really important, pi is greater than n sine 180 degrees over n, greater than or equal to, and it's greater, less than or equal to n tangent. Wow, look at that. If I could calculate that, and again, there's ways to do this that don't require knowing pi, this is going to work out really well. Look at that. I've got an upper bound and a lower bound estimate. Now this one right here is the circumference of the inscribed circle is 6, and the circumference of the circumscribed circle is like 6.4. I'll show you here in a little bit, but I think that's what it is. It's close to that. Now, as n gets bigger, the difference, this error here, this area, gets smaller and smaller and smaller. And as n gets larger and larger, the circumference of the inscribed or circumscribed polygon starts looking a lot closer to the circumference of a true circle. All right, so we've got the work here on the board. We've laid this all out. Let's go into MATLAB and let's see what this looks like.